basic concept. The key concept is vector space. I use V, the upper space W, U represent, and linear transform is from one vector space, for example V to W. I use this operator. This is to represent. If W is equal V, then we call this linear. This is the operator. And in the last class, I talk about the joint operator, which is defined as it's based on the inner product. And for vector transform, this is transform WV, and is equal to this star W, and T star is from W V, and it's also linear. And in the last class, I proved the existence of this operator, and it's also linear and unique. And I give proof in last class. So today continue to talk about from last class. Last class, at the end, I proved the spectral decomposition theory, which is that if for the complex vector space, I prove the complex vector space is normal, which means that T star T is equal to T star, and then you can decompose like this. If E1 and En exists, this also normal basis. And N is equal to this diagonal. This is diagonal. Can decompose, reduce to this concept. I also mentioned that for real inner product space, the condition is like this one. It's a joint operator, and also have this forms decomposition. From this, we can see that I and lambda I, like this one, it's an value, and we see that this is non-zero, and so lambda I is an value, and I is the vector. So, and the condition is sufficient and necessary from each other. So this is last class content. Just give some mention. From the spectral decomposition, we know that if the operator is normal in complex vector space, or in real space is a drawing, therefore drawing. Real space is a complex, and the whole space V can be decomposed like this forms. Lambda 1 to lambda m is a distinct and value. Can be decomposed. The whole space can be decomposed like this one. This is direct sum. And why is this? Because you know that this one, the diagonal matrix, and all the this is n. Also, all the vector can, all the eigenvector can become basis. So this is the null space is all the eigenvector distinct can unify the whole space with all the bases in there. And I also prove that for distinct eigenvalue, their null space is linear independent. So this is the sum. And also proved in the last class is that if they are normal, all the space in the null space is also orthogonal, which means that for every vector in all the subspace with 1 or some big M, they are orthogonal, which is with each other. Like this one. This is make sure by this condition. And also now see that if operator is self-joint, it's of course is normal. So by the decomposition theory, we can decompose the whole space in this subspace. M subspace. M is a distinct eigenvalue. It's very easy to prove this point. Next, I will talk about the two operators, which is important in our I think in engineer research. The first operator is the additive operator, and another is the isometric operator. First, I will talk about the additive. It's defined like this one. The operator must be self-joint. The first condition is must self-joint, and also for every V belong to the vector space, this condition must be satisfied. This is the definition of a additive operator. And it can equal to translate matrix operation. And I will talk about some equal statements and prove it one by one. First statement is T is additive. T is self-joint. five statements, I will prove they are equal, and I will prove from this order, and then prove E can induce A, so all they are equal. Yeah? So the logic is this prove this prove this, and this prove this, all equal. So, and first, T is positive. Of course, the condition, of course, T is self-joint. This is the definition, and also our value is non-negative. This can be proved from this one because it's equal to lambda v plus v. This must be bigger than 0 from this condition, and this is bigger than 0. So lambda is bigger than 0. So this proves this one. And I haven't talked about the square root. The square root means that if t can operator is equal to like this one, s is called the square root. If also s is also positive, we call s is the positive square root of t. And now I haven't proved s is unique, so I haven't used this sign to reduce the s because now we're not sure s is unique. And from the spectral decomposition, we know that for all the eigenvector E1, E2, En can be expressed like lambda 1, lambda n. So I define the operator like this one for each ER instead. ER, I define this operator, and this can be used because I from this prove this, and all the eigenvalue is non-negative, so I can use the square root sign, and I define this operator, and this operator is satisfied square root. We can prove it easily, and for t for this one. This linear division. This shares the same eigenvector with S, and the eigenvalue is just square root of the original t square root. And from this to this one, and also we from this one is that also. It can be expressed as this one. It's also self-joint, and also have all the value. You can prove that all the value this is bigger than 0. It's very tedious from this decomposition. So S is also positive from this proof. So this is even also prove this statement. square root. The positive square root is also self-joined. This of course is very obviously to reduce this limit. It's very obviously. And also from this statement is S is can prove this one, and S star equal to this, which is this limit means. And I can use like this one. So this limit can prove E also very obviously. And now I will from this condition to prove the first condition, which is as T star is equal to T star S T star, and use some conditions of this one and equal T. So it's self-joined, and also T V is equal to S star S V, which is equal to S V, and this will cause this become there from the inner product definition. This will become there. So all this is equal. They are equal with each other. And as you
I don't remember how the manual of the definition. Can I write down all definitions?
this definition.
I mean, yeah, even from the start, I don't remember how to
Okay. T star you do not remember
yeah, I
that.
don't remember how to become this thing.
As it right here.
I guess this was in the corner.
And
That's fine, that's fine. I write in the corner.
here. I have mentioned the L star. This is the T star definition. If we not, I will not talk about inner product. If V is for example, all the V and W is belong to the vector space. If V is determined, if W is determined and V the function for this is the function for V and it's a linear function, and I will prove that for every linear function for V, it can be expressed as this one. In last class, I proved it, and this W is unique. I use this unique operator. Of course, this V, this W may be not as this one. I use U. Maybe this is not as this one. So I use this operator to reflect this mapping. And last class, I proved the unique and existence, and also the linear property of this operator. Definitely, this is the condition. This one.
Yeah. The last equation is yes. This one is the V and V.
S star S V, and then comma V.
Oh, okay. Between S and V doesn't have any comma.
Yeah, no. This is inner product.
Yes.
Depart from
Okay.
here.
Yes.
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 So,
Can you give some intuition as the definition of conjoint?
self-joint.
I mean, like, more,
In matrix, you have some.
can you use the other side?
Yeah, self-joint is.
Maybe you can continue on exercise. Or maybe you can just.
spectral decomposition, we know that if T is self-joint, it can be expressed like the whole space can be decomposed like this. And
what's the lambda?
now is not space.
Oh.
It's not space.
No, lambda.
Yeah, as mentioned at the beginning of the class, it's from the spectral decomposition. It can prove the whole space is V can decompose like this one, where M1 to MM is distinct eigenvalue. So yeah, just said that. And as I proved in the last proof that there is exists the square root, positive square root, but I do not prove the square root is unique. Yeah, now I will prove the uniqueness of the positive square root. If T is S, for example, S is a positive. S is positive and also satisfies this condition. And from the, I want to see that if it is positive, it can use the spectral decomposition, and because it's self-joint, positive is self-joint, so S can be expressed for its eigenvalue, like alpha I E I, and I assume the whole dimension is n, and it can also express as this one. This kind of matrix form is diagonal, and I write like this one. This is eigenvalue, and this is eigenvector. This is eigenvalue, and so from the condition is that S E I is equal to S alpha I, and S Y S E I. Have this condition, and this is equal to T E I.
Alpha is a matrix. Alpha I is a matrix.
No. It's eigenvalue. This is eigenvalue. This is eigenvector. It's scalar. Alpha I is scalar, and also I assume S is positive, so alpha I must be non-negative. So T can try like this one, and from and which means that is like this. EI is eigenvalue of T, and alpha I square is T is eigenvalue, and this is eigenvector. Yeah. So if S is a positive square root of S, all the eigenvalue is belong to. If I use lambda 1 to lambda n to express the decomposing vector, then alpha I square must belong to, as distinct m, must belong to 1 of lambda m, from 1 m. And so this space is belong to, which which means that because alpha I belongs to this one, which means that because alpha ei belongs to null space of S I alpha I of this space, and if it satisfies this space, it's also in this space. So this space is a subspace of this space. Because all the vectors belong to this one, so this is a subvector space. And also it's like this one. Any question?
Why is this one then now this is minus alpha I is the subspace of that one?
Yeah, it's this space.
Why?
Because I have proved that if for example one vector is belong this space, it can express it like this one. Now I have proved that from the condition that alpha this EI is also belong to this space. So I prove because alpha is general, so all the space is this is the set proof. If you want to A belong to B, you must prove that for every vector space, A is also belong to B. Then A is that's the body. This one.
How did you go from the S alpha EI to alpha squared EI?
This one.
You can just move the S to.
I assume is a square root. I assume
No, I mean yes, yeah, I know, but I mean the last term.
This one.
No, that equation, the last term. How did you
This
find
one?
it? Yes, you just move the S to between the.
No. I will explain to you. And do you have question about this?
Yes.
This?
No. Yeah.
Just this one.
The last one. How
Last
did you?
one.
Yes.
Yeah. From this one to this one.
Yes.
Because this is scalar and this is linear.
Oh.
It can outside. Yeah. And use the second.
Oh yes, it's argument. Okay.
No question. This one. Okay. I prove that T can be decomposed the whole space like this one, and S is also can decompose like this because it's positive and satisfies the null space. Yes, if S have P distinct vector, vector, it can also decompose the whole space like this one. Yeah. No question because T is positive, is satisfied, is self-joint, so satisfies the spectral decomposition, and also that one this is must be belong is the subspace is the subspace of this one, and they are equal to V space. So I prove that one of the space must be equal to this one. Not so P is equal to M. For that they cannot be equal because the dimension they have the same dimension. So the null space vector is unique. It decomposes unique. So exists the unique x vector is positive, which is that x squared is equal to t, and I can use this signal to denote this one. So in the next case, like this one. Next, I will talk about the isometric operator. Next operator. This is positive. Isometric operator is S belong to V, which is their norms are equal. Like this one, which we said S is isometric operator. It's meaning the norms. After transform, the norms are equal. And I will induce some series if S is normal, and then this is equal. If it is satisfied by this function, I will prove that it also satisfies this condition. It's very good property because if UV are orthogonal, after transform they also orthogonal from this one.
What is S?
S is operator,
Operator?
a linear operator, and satisfy this condition. We call S is isometric, and from this one to prove this one, which means that number first level proof is in the real space. This constant equal to this one, or after this term, they have 4 atoms, they have 4 atoms. This one, multiply this one is the reduction, this one is the reduction. And so yes, after everything can be like this forms. And first I assume that it's a real space, so they can change order in this in real inner product. They can change order, so this 4, this is none. So this one is equal to this one. Yeah, in real space. And then I continue. This is equal to SU, SV, multiple SV square, and then SU plus SV square. Yeah. This is equal to this one, and equal to plus U plus V. can be, after you reduce, it can be equal to u v. So, and this is for the real inner product. For the complex vector, it's the same, and it have a little tricky transforms. You can also class this form like also as IV. I is the virtual number. It's IV. Remember, it's just like this one. And this formula is equal to that one. And the same transform tedious. And also that if the S matrix, they also have the condition that S star is equal to I. And this can be proved with this condition because SU SV is equal to S star SU V, and also equal to this one U and V, and these two can combine together. I have S star S minus I U equals to this one, and UV is arbitrary vector. So S star, I have proved that S star is must be 0. Yeah, because it's arbitrary, you can also use you can let V is equal to S star S I U. Then they are the same. You can also have this condition. And so S star S is 2 square I. And from this condition, as we should see that S is injective, because if V is non-negative from this one, its value must be non-negative. So it's an injective object. I will talk to decomposition. Yes, it's over this series. I have talked about the two operators, and for the general operator, I want to decompose the operator. I will prove that this operator can be expressed like this and this one. This one is a positive operator. I have proved that this is a positive variable. It's all called exists the square root, and also the S is the isometric operator. So for the general operator, it can prove that it can be decomposed the two operators together. First is positive, then is isometric. The general case, and this proof is a little tedious. Do you want to listen or not? Little tedious. I can show that.
It's okay if
You want to say okay. First, I will prove a lemma. From this one, can be transformed Then escape the scam star. Come with this one causing self-joint. This one, and which means that which means this one.
So which one is self-adjoint again?
Self-joint?
Self-adjoint.
You mean which the meaning of self-joint?
Which one? Like,
Because this whose operator is self-joint. It's also positive.
okay.
Yeah. So it can decompose. Like this. Also proves the uniqueness in the existence. So it can use this one. So this existence is here. And I define linear transforms as one is linear transforms from first step we define one from range star G to range G from this space to that space, and the condition is equal to this one. V is equal to TV. The value is equal to this one. This mapping, and also this is the domain, but this can be not. I will prove that it's definitely is a linear map. From this one, there must be for the mapping definition. If the domain is equal, their value must be equal. Yeah. For x on the mapping, if x1 is equal to x2, fx1 must be satisfied x2. This is mapping. Yeah. So this condition just define the value, but also maybe existence. For example, t star t v1. V2, also maybe have the exist V1's this operator is equal, but TV1 not belong, not equal. Yeah, have this possible. I will prove that this cannot satisfy. If this is equal, this is also equal. So this is a linear map, but this is a map. This one is equal to this one, then from the lemma, this must be equal. From lemma, this is equal, and if this one this is equal to t star t v1 t star t v2, and if the value is equal, then t TV1 is equal to TV2. So this proves that it's surely mapping from this condition from the lemma. So it's a mapping. The linear proof is very that it's easy, and you can from this condition prove the linear and control it. So S1 is a linear mapping from this range to this range is a linear mapping, and also from the condition we know that S1 T star T V equal to TV and equal to T star T V. And yeah, I use U to denote this whole S1 U is equal to U. Yeah, whole space. S1 is injective mapping from this condition. Because do not exist U is not equal 0, that SU is 0. This condition, so it's injective. S1 is injective, also a linear mapping. I'm not sure if you remember, I teach in the first 13-minute class, the linear mapping. If it's injective from one space to the last space, that dimension are equal. These two dimensions must be equal, which means that it's linear map from V to W. Then I have proved that dimension V equal to null space of T is belong to this one. Now T and now over dimension range. This is equal, and I will prove this one. Now it's now surjective, so this is equal 0, and so this two must be equal. So these two ranges it have the same dimension. The whole space is V, and now if this dimension is without this dimension star T is equal to dimension of range T. Yeah. So the whole dimension is V. Suppose we have a dimension whatever, and this can prove that the dimension of the range is star T orthogonal space. This one orthogonal space also equal to range T orthogonal space. This must be equal. The whole space is equal. And also orthogonal space also have the same dimension. It's very easy to do that. And I defined a linear mapping. First, I suppose this A has orthogonal basis from we have dimension M. I can find orthogonal basis, and I also can find orthogonal basis in this one, F1. they have same dimension. So the Fm, and define a linear mapping A1, E1, Am, yeah, is equal to A1, F1, Am, Fm. I demand this operator. Yeah. And this operator is domain is in the orthogonal in this space, and this space. The whole space can be expressed like read T star T and yeah, the space can be expressed as one. That space and they are orthogonal space. So I define the SF operator is that of S operator is like this one is equal to this one U S2 V, and for every vector UW, for every vector V, it can be expressed like this part and this part, they are together. For this, assume U is belong to this subspace and W is belong to this subspace, and so V can express like this one. And I define the S operator is like this one. We project the S, U, and W like this one. So the final proof is that sorry, I missed the order. And the final is that I have must prove this is isometric. Yeah, this is I will prove this is isometric because it's projection to this space, and this space is to this space, and S2W is this space. There are two spaces orthogonal. So as we square from the Pythagoras theory, it's going to be like this one. And this I already proved. S2 is defined like this one. It's also, it can be proved like this one, which is equal to W, no, V square. So SV norms is equal to V norms. So S is the isometric operator resistance. So every first I project here. So for every which belong to like this one. U is in this subspace to this one. Can be expressed like this. And S is also isometric. And this is positive. I want to mention that I have a tuition that for this program may be tedious, but I want to have some tuition that for every complex vector, we can express it like this one. similar like this decomposition for every this is number. Yeah. Also matrix positive. Yeah, for every value. These are similar. And this is the polar decomposition for the vector. Polar decomposition of vector. Decomposition of matrix transforms. And the last decomposition I want to mention is maybe we use very commonly is SVD, singular value decomposition. It's used in matrix completion very commonly to argue the statements. And we know that for every operator it can be decomposed like this one. And this operator is positive, yeah. So it can be expressed like it's self-drawing and satisfy spectral decomposition. It can be expressed. There exists this is all of course all the term is under 1 and n. So positive satisfy the self-drawing. This can decompose like this forms, and because this value is the singular value of t, and for each one, v space is the arbitrary vector of space. This can express like A E1 yeah, E1 En is also normal. Yeah, this can express like this one. The base is the decomposition. And after I use this operator, this R T V this one, this forms the operator. This is the scalar just outside, and this can be expressed like this one. Okay. Lambda I can be expressed like this one. Because in the eigenvalue, expressed like this form. So now I use this form, the S operator on this whole part. Yeah, I have made the linear velocity. Lambda I and S I. Yeah, this is scalar control outside, and I use the indicative and multiplication and draw the coefficient outside. And I have proved that if S is isometric, they are, if E1 to En is isometric, so after the isometric transforms, all the vectors must be orthogonal to each other and also orthogonal. That's En. Also orthonormal. Keep norms. They keep norms and non-zero, and they orthonormal with each other if the corresponding space have approved. So these are all the basis. They are also the basis of orthonormal. I use F1 to express F1 to Fn, and so this can be expressed like this. All the Fi is also normal with each other. This is the forms of SVD decomposition to linear algebra. The complex forms like this one, singular value on every vector can decompose like this, and so it's it's transformed the orthogonal space to another. And we know that from the spectral theory, we can decompose use the eigenvalue to express the non-space, such as the eigenvalue to express the whole space like this one. But for the general case, it cannot. Even for complex vector space, I will prove that complex vector space can have eigenvalue of maybe distinct eigenvalue, because after they can use. But in the next class, I will prove that how we can use the eigenvalue to decompose the whole space for the general. And the spectrum is for the self-joint. But for the general space, how can we decompose them? We cannot use these forms. Lambda 1, this form decompose the general case. I will implement another form to decompose the whole space. Any questions?